In this video, I will show how to use the trapezoidal approximation to estimate the area under the graph of a given function on a given interval. So in this case, we have a square root of x cubed plus 1 on the interval from 1 to 5. And let's sketch a generic graph just to remind ourselves what is trapezoidal rule. And if we have some function f, in this case on the interval from 1 to 5, and to find t4 means n is equal to 4, and that means delta x is equal to 5 minus 1 over 4 equals to 1. That means we divide this interval into 4 subintervals with numbers 1, 2, 3, 4, and 5. And each area in one of these 4 intervals will be estimated using the trapezoidal rule. So let's draw these trapezoids. And the area of a trapezoid is the average of the bases times the height. So let's assume that we have the outputs of a given function. And actually this would be y1, this would be y2, y3, and y4. And the formula that we are going to use is the following. We're gonna, since the height is 1, we're gonna just factor it out. And now we have the average of all the heights. So we can factor out 1/2 out, or since the number is small, we can actually just write it out here. So we have the average of y1 and y0. We have the average of y1 and y2. We have the average of y2 and y3. And we have the average of y3 and y4. Now, when factor out 1/2, the expression in the parentheses can be simplified like this. So as long as we know the outputs of the function at 1, 2, 3, 4, and 5, we can plug it into this formula. So what is y0? y0 is f of 1. So it is square root of 2. What is y1? y1 is f of 2. So it's square root of 9. 3. y2 is f of 3, so it's square root of 28. y3 is f of 4, so it is square root of 65. y4 is f of 5, so it's square root of 126. Now each of these can be approximated. Let's do up to 3 digits. So square root of 2, I'm just going to compute it on the calculator, is 1.414. 3 is 3. Square root of 28 is 5.292. Square root of 65 is 8062, and square root of 126 is 11.225. And now we just plug it into the formula. So t4 therefore is equal to 1/2 of 1.414 plus 2 times 3 plus 5.292 plus 2 times 8.062, I lost the 2 over here, and plus 11.225. Again, I'm just going to use a calculator to compute this. So 1.414 plus 6 plus 2 times 5.292 plus 2 times 1.414 plus 2 times 3 plus 2 times 5.292 plus 2 times 8.062 plus 11.225, and divide all that by 2, we get 22.674. So this is a trapezoidal approximation of the area using 4 intervals. Now, how do we estimate the error in the approximation in part A? Well, first we have to recall that the upper bound for the error in trapezoidal method is less than or equal to this expression. Well, we know B, we know A, so A is 1, B is 5, we know N is 4. The only thing we don't know is K. What is K? K is an upper bound for the second derivative. So to find K, we want to find the second derivative of this function and take its upper bound on the interval from 1 to 5. Now, in this procedure, we don't have to do it by hand. We can just, take use some technology and graph the second derivative of a given function and just visually estimate its upper bound. So here's the graph of the second derivative. And just by looking at it on the interval from 1 to 5, we can tell that the upper bound is happening at x equals 1, and it's definitely less than 1.4. So we can set k to be equal 1.4. That means now we have all the ingredients to plug in into this formula, and here's the result. So for k we plug in 1.4, b is 5, a is 1 cube divided by 12, and squared n is 4. So we have this expression, so 5 minus 1 is 4, 4 cube divided by 4 squared is just 4. Reducing it, so we basically have 1.4 over 3, which is 4.67, 0.0467. So which means that this approximation may not be that accurate, right? So now the next question is, what if we want to improve the accuracy and want it to be accurate to within 0.0001? So that means we want to find n such that this expression is less than this desired accuracy level. And we already know what k is, b and a, so the only unknown here is n. So to solve for n, we just isolate n squared on one side, and replacing k with 1.4, replacing b minus a with 5 and 1 gives us 4 cubed, dividing it by 12, and dividing it by 0.0001. So the right hand side of this inequality is $74,666.667, and taking square root of both sides and only considering the positive solutions gives us the following result. N must be greater than 273.25, which we have to round up, and the answer is 274. So in order to achieve the accuracy within 0.0001, we have to choose N to be 274.